So, good morning, everyone. I've spent the last 20 years of my career in Canada, and in Canada they have these cultural laws that say if you're in Canada, you're a bookstore or you're producing TV or movies, you have to have a certain percentage of Canadian content in them. And so I thought coming here I'd have a little bit of French content in mine, and it was on my laptop and we had technical difficulties, so I don't know if you can hear this, but this is my French content. Does anybody know this song? Maybe Paolo. It's old. What? L'été indien. Okay. And I want to use this to teach you a little bit about when summer starts in different parts of the world and when summer ends. So I'm from North America and Canada and the US. Summer ends today, period. There's no debate whatsoever about that. First Monday in September, we're done. So the summer school, I was a little shocked to see it's not in summer. So I apologize. I have to go home tomorrow. So I won't be here the whole week. But you have to listen to Joe Dessin. But I'm hoping you'll enjoy the presentation that we have. And hopefully that doesn't keep on going. Okay. So I'm going to tell you a little bit about data lakes. And so as I said, I've been in Canada for the last 20 years, and this last year I moved to Boston, to Northeastern University. But the work I'm going to talk about is work that comes from my group in Canada, and in particular my two PhD students, Fatima and Eric Zhu, who just graduated a few months ago from Toronto, as well as my postdoc, Patricia, and our colleague, Ken Pu, in Ontario Tech. And I thought I translated, oh dear, this is going to be a problem. I thought I moved over the key, and I think I only moved over the PDF. So what is a data lake? I think you all have heard this term and have seen it, but probably nobody can really define what a data lake is. But people are finding a need to store structured information in resources and in repositories other than data warehouses and database management systems. And they're finding that need for a number of different reasons. And the reasons include the need to be able to ingest new data at very, very fast speeds, at real-time speeds, where you can't get it into a warehouse or a database management system. They also need a data lake because they want to be able to incorporate unstructured and structured data all together in the same kind of repository. So I'm not going to actually define what a data lake is, but I'm going to give you some examples of what data lakes are. Basically, a data lake is some kind of storage system that supports data in different formats with or without metadata, and where the metadata itself may be in different formats. This is going to be a problem. Just 1 second. Is the only way to scroll? Does anybody know how to move forward? And présentation. Activer le mode panorama. This one. This one. No.
Yeah.
There we go.
Yeah.
Okay. Oh, no, but it's... Okay, so if I do this one? Yeah. Okay. All right, so I'm going to give you a few scenarios where people actually use data lakes. And these scenarios come from a survey that we did, that we put out on SurveyMonkey, with for data lake professionals who are actually using in their own practice, their data science practice, different kinds of data lakes. And so one of our respondents was a global investment bank that had over 10,000 employees. And they decided to use data lakes back in 2008 when they found that they needed a way of finding all the data in the organization really fast for regulatory purposes. And what they found was, back in 2008, they weren't able to find all their data. They were looking, they had to go to Fred's C drive, and then they had to search through Mary's email to find all the data that they had. So this kind of inspired them to create a data lake where they hoped they could actually find data very quickly for analysis. Yeah, so you get, even if you can ingest this data from open data, and this is an actual data set from open data that has information on homicides, it has information that you can kind of understand pretty easily, but it also has information that you might not understand. For example, what does vector or coordinate mean in this data set? And what you find is, from open data especially, the data comes with metadata, but sometimes that metadata is just free text descriptions of the data set or of how it was collected, right, the methodology used in collecting it. And often it doesn't have enough information to correlate with things like the header information. So you may have no idea what vector actually means in this data set. And of course, data lakes can be dirty. So this is information from the New York City open data, and it's information about taxi cab fares. And you can download this from the URL that I have here. And clearly, there's a data quality issue with this data. It has cab fares that are over $600,000. And it has a lot of them in this data. So the data itself may be dirty, and we need systematic ways of understanding when the data is of poor quality. Because if you're doing some kind of analysis and don't realize that this is in here, your analysis is going to be way off. You're going to get huge amounts for fares. So in our survey of data lake practitioners, and in surveys that consulting agencies do as well, data cleaning remains one of the most important challenges in a data lake, because companies want to ingest this flexible new information, but they also want to be able to clean it and rely on it for decision making. And so we'll look at, so in data lakes, some notion of unit testing for data lakes, data sets is needed, and kind of adopting, I have to talk faster, I think, sorry, for data sets, kind of things like from software engineering to make sure your data has a minimal data quality in it. And data lakes are evolving. So this is information on US imports from China, a very relevant topic right now, where each dot represents the size of a particular commodity, how much the US imports that particular commodity from China. And this plot, data analyst probably wants to know what is the raw data that was used for this plot. And so, and in particular, which version was it based on? Is this from the first quarter of 2019, or is this earlier data, and so forth? So in data lakes, because this data is getting ingested at very fast rates, you often get different versions of the data set, and you want to be able to understand which analysis was based on which version, so provenance information. And you also need to do this even when metadata itself often is disassociated from the data, and sometimes the metadata can get deleted even before the data gets deleted. A third scenario we have is a data science research institute, a much smaller company than the bank that we were talking about before. And here, the data sets are stored in some kind of distributed file system. And they're using the data lake in a very different way. They're using the data lake to store the inputs and outputs of different machine learning and data science pipelines. And so for them, the data lake really is a file system, right? And their biggest problem was in the duplicate data sets that they get. Because each analyst, when they're doing some kind of process, they start with a data set, but then they might clean it, they might add an attribute, they might transform some attributes, and so they end up with different versions of the same data set. And often those versions are only documented by their file names. and the file name might say Fred did this on this date, da 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 da. And usually it's very hard to understand for the next analysis which version of the data set you should be starting with. All right. So data lakes are very diverse. This is all the data set formats in data.gov. So there are hundreds of different formats from JSON, HTML, CSV is a very common format. You don't see as many of these formats inside an enterprise data lake, but you certainly see a lot, at least dozens of different formats in a data lake. And the data lakes themselves, because they're so diverse, ingestion and extraction is the task of bringing structured data sets into the data lake. And it's the task, ingestion is the task of taking already structured data sets, for example, parsing a CSV file or parsing a Parquet file into a data lake. Extraction has to do with taking unstructured or semi-structured sources and turning it into a structured resource that you can ingest into the data lake. And there's a lot of research now on doing this at scale and in real time, so being able to ingest things very, very quickly into data lakes. In addition to the formats that create diversity, the sources of the data actually create diversity. So this again is data information from data.gov, and these are the data publishers. And the data publishers add diversity because they each have different conventions for metadata standards in particular, and also conventions in terms of the formatting and how well they format their CSV files and so forth. So a final example scenario of a data lake is a large hospital. This is a hospital in Toronto that had more than 1,000 data sets, and 1,000 doesn't sound that big to database people, but what they wanted to do was to take their electronic patient records. They had an EPR system running in the hospital, and they wanted to understand how they could augment those records with these other data sets. So they actually wanted to join and union the electronic patient records with new data sets that they had either purchased or created within the hospital setting. So in this context, they wanted to use their data lake for actual data integration. They really wanted to augment an existing very well-structured source with new information. And so the tasks that I've kind of outlined here are ingestion, extraction, kind of bringing data into a data lake, metadata management, which includes creation of metadata and cleaning of metadata, data cleaning, data integration, data discovery, and data versioning. These are some of the tasks that you see within a data lake. And some of them, like cleaning and integration, you see within a regular database management system, but others, like discovery, are something that you don't see in a database management system. In a regular DBMS, you have a catalog, right? And you know what data is in there. And you can search the catalog, you have some consistency. In a data lake, actually finding the information can be very difficult. So another important thing about data lakes is that the performance metrics are a little bit different than what we're used to in plain old data management. So we're still interested in scalability. So the size of these data sets still matter. So when we're testing our techniques as to how well they perform, one of the independent variables will be the size of tables that we're working on. But just as important is something that we call throughput, which is the ability of a technique to apply to many different data sets. And so since in a data lake I can have millions of different data sets, do my techniques actually scale up to that number of different heterogeneous data sets? Another dimension is the robustness to heterogeneity and the applicability of different techniques to data or metadata that's in different formats. And then because of the scale of data lakes, we're often going to see techniques that use approximation. And so accuracy becomes an important measure here. And being able to measure accuracy can be challenging because it's not as simple as it is in machine learning where you have simple precision recall. Actually defining what the gold standard is and so forth can be quite difficult. So what I'm going to drill down on is the discovery aspect, and I'm going to spend most of my time talking about new discovery techniques within data lakes. Let's see. So to begin with discovery, you have to say, how am I going to specify what data I want, right? How do I specify a discovery query? And there's two basic ways. One is to search by keywords, right? And this is actually something that Google supports right now. So if you Google the phrase dataset search, you will get a beta Google service that lets you search data. And I would encourage you to do that. And if you type in, for example, the word wine into the dataset search, you'll get hundreds of data sets back because it has a lot of data sets about wine. If you type in something like Cabernet, Merlot, Baco Noir, which are three varietals that they grow in southern Ontario, you'll get 0 answers. And the reason is that Google is only searching the metadata. And so if you're interested in a specific set of wines, you're kind of out of luck. You have to be able to describe them at the metadata level in order to get things back. And Google is doing it this way, and they're doing kind of what Google always does, is they're improving their search by training us to make their search better. And so they say, if you want to register your data set with Google, then you need to add in metadata from schema.org that makes it searchable and findable, right? And that works really well because I think probably for everyone in this room, if I search for a picture of you, I will find it. And that's because Google has taught you to tag your pictures of yourself, right? You won't find a picture of me because I never tagged a picture of myself. And trust me, there are thousands of pictures of me on the web. But just because on my webpage I've never tagged one, you won't find it, right? So Google does this. So their algorithms aren't that great, but their ability to train us to feed their algorithms is impeccable, right? And so that's how they're doing dataset search, which is great for me because I want to do the other kind of dataset search, which is by value. And so I'm going to talk about techniques where if I'm a data scientist and I have a data set of interest, and it might be a data set that has a set of wines I'm interested, or it might be an environmental data set that has a set of environmental indicators, very specific ones that I'm interested in studying, then the data scientist can say, well, in the data lake, are there any other data sets that join, meaning have exactly those same values in it with my data set? And so we call this joinable table search. And I'm going to talk about, we had a 2016 paper that introduced this problem, and then there have been a couple follow-up papers that I'm going to talk about as well. In addition to that, in addition to joining, you might want to find other tables that union with yours. So maybe you have a data set on those environmental factors and you want to find additional tuples, essentially, that follow a similar schema and that are relevant to whatever you're studying. So that's the union table search problem. And then in addition, there's older work that does kind of attribute search. And there's work, InfoGather is an older work that lets you specify entities that you're interested in. So for example, you could say, I'm interested in companies, and I have this data set on companies, but I also want to find the CEO attribute for those companies. And they do it, though, by matching on the metadata. So they try to find any other attributes in the data lake that have a CEO or a column that refers to CEO using schema matching techniques. And there. So that's my whirlwind introduction. Are there any questions at this point? I'm going to kind of drill down now into some of these techniques. All right. So as I go down into data discovery, I'm going to start by actually telling you a little bit more about the characteristics of data lakes. And because I'm an academic, companies don't actually give me their enterprise data lakes. So when I started studying this problem, we decided that we were going to look at open data as a specific kind of data lake, and one that we can get our hands on and study in great detail. So I'm going to tell you a little bit about that before I dive deep into the techniques that look at table join and table union. So there's lots and lots of open data out there. So in the US, it's data.gov, but there's a European open data movement, and almost every country and almost every city actually has open data associated with it. And the open data is important because a lot of these governmental and non-governmental agencies are adopting open data principles. And there's 8 or 10 principles, depending on which organization you follow. But some of the principles for open data are that the data that you make open should be timely and complete. Timely and comprehensive, sorry. It should be accessible and usable, meaning it should be in some kind of format like CSV, some open format, not Excel, which is a closed format. It should be complete, and then all public data is made available. And it should be primary, and primary means that it should include the original data and the metadata about how it was collected, the methodology used for collecting it. And if you look at these, if you actually achieve these principles, then this data is going to be incredibly valuable for data science. And governments, including the US government under Obama, adopted these principles and said, well, if we're collecting information using taxpayer money, then we're going to make that data available to the taxpayer. And the idea being it should spur economic growth and so forth in things. So, and if you look at this data, well, and this data also is easy to get because it's not hidden behind web forms. There's actual APIs that data.gov and other places support. There's one called Socrata and another one called CCAN. And you're allowed to crawl these without breaking any rules, and they want you to crawl these and download the data. And you find, if you do this, that the open data is deeply connected. If you just take it as it is and do joins on it, just equality joins. Here we've taken one table, which is that yellow table, and joined it with everything we could find that joins with it, and up to the 4th degree. And you find that the values in it actually join, and you get this rich, deeply connected structure, graph structure of data. And the open data is, first of all, it's often wide, with an average of more than 16 attributes. And the attribute cardinality follows a Zipf-ian distribution, meaning that there are some tables that have thousands of attributes, and then there's a whole bunch of tiny, skinny little tables as well. It's deep with an average of 1,500 values, and again, the depth follows a Zipf-ian, and that's what I plotted over here. And you'll see that the largest tables in a crawl that we did, this actually is Canadian open data, because we were up in Canada at the time. The largest table we found was 22 million tuples. But of course, it's Zipf-ian, so there's lots of tiny tables, and then some very large tables. It often has no or incomplete headers, that meaning attribute names. Sometimes there are attribute names. Sometimes the attribute names are 1, 2, 3, 4, 5. And sometimes they're in the metadata, but if they're in the metadata, they're often hard to bring back over to the data. And they're published often in comma-separated value, CSV or JSON formats. And it's growing exponentially, the amount of this data that's out there. So this is a video, which I'm going to see if the video is going to actually play on Benny's machine, of a tool that we built to be able to search this open data. And so in this, I'm going to talk through it as it plays. But we start with, there is metadata that people can look at to view at a high level what the data is. And you can do keyword search on that. But once you find a data set of interest, then I want to actually explore things using joins. So that's what this video is going to show you. And it's working. Excellent. So this is Canadian open data that I can browse. But I can also enter a keyword. I'm going to enter NSERC, which is the federal funding agency in Canada, and for 2004. And I find information about partners. These are industrial partners that have sponsored NSERC grants in Canada in 2004. Now, I can click on a value and find everything that joins with it. And those were the grant IDs that I just clicked on. So I found actually, this is the awards data that has the amount of the awards, and it joins with the partner data that has the industrial partners. So I just joined on those two. And so now I have the university that was given to, the amount of the grant, as well as information about the industrial partners, Bell Canada and so forth, that sponsored it. And now I can write any kind of SQL query that I want to here. So for example, I can select these partners, part institution établissement, because we are bilingual, as organization, and we can sum up the amount of the award as the NSERC amount. And I'm going to do a group by, from the table T, a group by on the organization, right? Sorry. So now I find for Bell Canada the total amount of awards they've received in this year, and for different organizations I've summed that up. Now, I've looked to find other information about these companies, and I found another data set that is from Elections Canada, and it joins. And what this data set has is for each one of these organizations, Bank of Montreal, Bell Canada, it has the contributions they made to political parties in 2004, in the same year. And so the Liberal Party and Conservative Party, it has the address information and then the monetary amount of the contribution to the political parties. And so now I can select the organization, the NSERC amount, and the amount of the political donations that they got. And again, I can do a group by and sum up all the contributions to political parties. And so I'm going to sum that monetary amount there and call that contribution. And now I'm going to get back another table that has just, it's going to say Bell Canada, it received this much from NSERC and it donated this much to a political party. And actually I included the party in there, so it's going to say Liberal or Conservative or NDP in the column itself. And so now I can take this table, if I'm a data scientist, and look and see if there's any kind of correlations or other interesting patterns in the actual data. And so I can take this data and download the data, and then I can visualize it. And if I visualize it, I find out there is some clear correlation here, right? The more NSERC awards you get, the higher you are on the amount that you've contributed. And of course, it's correlation, not causation. I'm just plotting things here. And I can drill down and plot for Liberals and Conservative the amount of the award and so forth. The Liberals were in power in 2004. And the reason that I used 2004 in this demo is that after 2004, this data disappeared from open data and the Conservatives came into power. But again, I'm not saying there's any correlation there, causation there. But what I want to be able to do this kind of data science on open data, right? Oh, the radius is the, what is the radius? I used to know that. It's the amount, it's one of these two amounts, right? Because it's going up linearly, yeah.
Is it the maximum and the minimum?
I've forgotten what the radius is, sorry. Yeah, because I only had 2 values in my table that I collected, right? So I don't know, it might be a repeat of one of these values, yeah. So.
And just one question, Jeanette, you have showed an example in which we use SQL, but in data science we can use Python or R, and
Yes.
they want more complex transformations.
Yes.
So what?
I completely agree. So this demo was from 2017, and it was on top of Postgres, so we used SQL. And I think today, if we did it, we would use some kind of Jupyter notebook as the interface so that you could enter Python or something like that. And there's a couple interesting notebook projects that database people are doing. They're not in my slides, but one is by Boris Glavic called Vizier with Juliana Frady, where they're adding provenance into a notebook. And so they can kind of let you do this kind of thing and then and trace the provenance of it. So yeah, that is a downside. This demo works well at a VLDB or SIGMOD conference, but maybe not in data science because of the SQL. So in order to do that demo, what I needed to be able to do was take a table like this, and this is a table from actually the UK Open Data, that has information about greenhouse gas emissions in around London. And it may have attributes in tens of thousands of tuples, and I want to be able to take that table and find other tables that join with it on a certain column. And so the data science question is, how can I find more features for my model of CO2 emissions? So suppose I'm actually trying to figure out if any of these attributes or features predict CO2 emission, which is the kilowatt hours there. And I find out I don't have enough attributes. To get more attributes in database terms, that's the join question. Find tables that can be joined with the query table. And to have as complete a model as I can, I actually want it to join on all of the values, right? I don't want to leave things out if I don't have to. So I want to be able to state a particular attribute, say here borough, and find tables that have those values and have additional attributes about the borough. And so here might have population, the unemployment. This column actually had the female unemployment as a number as well. So I'd like to be able to find tables like that in this massive data lake. I also might have a data science question that says, does my analysis generalize to new regions or new sectors? So suppose I've built a model of CO2 emissions based on this data. Can I test to see if that model actually works in other areas? And so that corresponds to the data management task of finding tables that can be unioned with a query table. Now, as I'll go into in union, the definition of unionable is unclear, right? The definition of joinable is pretty clear. It has to have the same values in it. So I know what it means to join, but to union, I might, just eyeballing this, say that the fuel type and commodity, it looks like the values in there are pretty similar, right? Kind of looks like they might be unionable. The borough and the county information, they don't overlap at all. But from my knowledge of borough and county, they're both regions about the same size. Maybe they're unionable. But that's a semantic thing. And then sector, the sector and sect type, they have lots of overlapping values. So maybe the overlapping values does indicate some notion of unionability. But I have to make all of that precise in order to define unionability. And importantly in these data lakes, one of the reasons that I was talking about open data is because I wanted to use it as a way of studying other data lakes as well. And what we find in our work, we used open data, which is our crawl of open federal government data from English language governments. We also looked at web tables. Are you guys familiar with web tables? I don't have a slide on it, but in web tables, there's been a number of different research groups who have looked at the common crawl on the web, and they've applied information extraction techniques to pull out structured tables from the common crawl. And they've done this in different ways. There are some groups that do it using visual cues of how the tables are rendered. Others parse the HTML and look for things. And so there's a whole body of work on pulling out web tables from the common crawl. And one of the approaches is called the WDC3 Web Commons corpus. There's another one from the Dresden University as well. But here I'm showing the WDC Web Commons crawl. And what they have done, they've created, I don't have the number of tables. Actually, I think their web tables has over 50 million web tables in it. And you can kind of view that as a data lake. But it's a little bit different than the open data lake. And it's different in that the tables that it has tend to be smaller. The pointer or something. The open data, they tend to be quite wide, and they can be quite large, up to 22 million. The web table data, because these are pulled out of web pages, usually they're relatively small, right? They're designed for human consumption, right? I might have something that has all the countries in the world, or a whole bunch of companies or something like that, but the largest one that they have is 17,000 tuples. And we compared this with an enterprise data lake, and I'm a little cautious on calling this enterprise data lake. This enterprise data lake is 116 tables as a subset of MIT's 24,000 table data warehouse. And this is the data set that's often used in the Data Civilizer project, which is an MIT project for their data lake work. And we just wanted to compare them to see if the web tables and the open data, which are open data lakes, resemble in some aspects the enterprise data lakes. And what we found in enterprise data lakes, not surprisingly, they're bigger than web tables but smaller than open data, right? But each table itself often has more. In the open data and web tables, often you get lots of these little tiny tables that might not be of that much interest. And the last column there shows the number of unique values that you see in these data lakes. And I'll tell you in a bit why I'm interested in that number. But for the time being, you can see that the enterprise, the vocabulary used is much smaller than it is in open data and web table data. The vocabulary used, the words that you use inside these tables tends to be massive, and so it's much more heterogeneous. But importantly, they tend to follow these Zipfian cardinality distributions. And the distribution is a little bit different in web tables than it is in open data, but you do have this skew in things. And the reason I'm putting this up here is because our techniques for doing this search have to be effective even if the data has these characteristics, has this skew in them. And I'll show you why skew matters for these techniques. So that was kind of my whirlwind introduction to some of the open data lake, and also how we want to be able to do some discovery over these open data lakes. And now I'm going to go kind of into some of the techniques that we're going to use for these. Any questions? Feel free to ask a question. Yeah.
So lots of data coming in from various sources. How are we managing the single source of truth in a data lake?
We're not. We are allowing multiple sources of truth in a data lake, and I think you have to. Even in a data warehouse, people have talked about how one company doesn't always have one source of truth in a data warehouse. You have to be able to live with multiple versions of the truth. Yeah. we're not.
So how would the decisions be affected by, or how would we use the data? How do you
Yeah, so this is kind of a metaphysical question on how, because companies more and more want to use open data, they want to use social media data, they want to use in order to do decision making, and by its very nature it's going to have contradictory information in it. And so I think once you get up to the decision making process, I think you have to take that into account. My work is at a much lower level, just letting you find the different bits of consistent or contradictory information in there. Yeah.
Well,
Yeah. Sorry.
Probably it depends on the goals of your activity. I mean, it's
Yeah.
the same thing as asking the balance of your bank account.
Yes.
When you really need the precise figure, or looking for a good hotel where you appreciate suggestions and so forth. I mean,
Right.
the quality of and the precision of the result depends on what is the goal you have in mind.
Yes. Yeah, that's very true. And also, I think in data lakes, people are using, for my initial scenarios, they are using data lakes in activities that require exact answers, like my bank account, or what is my exposure to Lehman Brothers, right? Where they actually want to, in their decision making, understand what's true and what's not true in that. So yeah, in other tasks, in machine learning tasks that you hear a lot about these days, like you're trying to just predict the type of an image and things like that. A lot of the way that the data is used is in an approximate way. So things like the integration itself becomes kind of a latent variable, and then you're just predicting something that is supported by the majority of the data, right? And so that type of a task, you kind of ignore the inconsistencies that you have down in the data. But other tasks that we're supporting through unions and join, you actually want to have correct data in there, and you'll have to clean it. Were there bottles of water here somewhere? Could I grab one? I thought I saw them on there as I came in. So there was another question over here. Yeah.
So I was wondering about Unionability.
Yeah.
So would you consider two data sets of different versions of one data set be unionable?
Yes.
Or not? Because semantically and syntactically they are probably a nice fit.
Yeah.
But maybe from a data science point of view, we might not want to join all union.
Yes. Okay. So I'm going to give you precise definitions of unionability coming up. And one of the flaws in my definition is that the table that if I give you a table, the thing that it's most unionable with is itself, right? And so my definition of joinability and unionability don't include any notion of new information, right? And that is a very interesting open research problem. Can I find tables that are unionable and have the most new information that contribute the most to what I have, which would downgrade the versions of the same data set? Yeah, but the definition I'm going to give you, the answer is yes. A version of the data set will be unionable with it. Yeah.
While you were just looking for new, similar tables to just join with your current table, so you mentioned that you don't like to just put different features aside and just use one feature to join. So I was wondering, how do you consider all of your columns and features that you have to find a similar table?
Oh. Well, I'm not sure I understood your question. Let me try to
So in the slide that you showed that you're looking for similar tables to join.
yeah.
So you said you don't want to put every column aside and you just use one column to find similar tables. Or maybe
Oh,
misunderstood.
I think you misunderstood because actually I am doing that.
Okay,
So
so you're using one column.
yeah, at this point I'm using one column, and the user's telling me what column it is.
Okay.
Yes, and let me tell you how I'm going to do it, and then you'll see why doing it on multiple columns is very hard and an open problem. So yeah, yeah.
Also, this column would be changing, right? I could make join with this column and then make another join with another column, or it should be one.
Yes. Yes, I want to be able to join, yes. If this is my query column, I want to be able to join, find other things to join on that. But then I might take another column and be able to join on that. Yeah, so I want to be able to do all this, and I want to be able to do it fast, even if there's millions of tables in my data lake. Yes. Yeah. Yeah. Any other questions?
So maybe it would be a solution of multiple.
Yeah.
Of multiple join, multiple column join. You could have it in multiple.
One at a time, yeah. So doing it one at a time is much easier than if you'll see as I go through this. If I give you two columns, it would make more sense if I had like this column in year or something. Can I do it on both of them? And I'll explain why it's harder once I go through the single column one. Yeah. Right. So I have a query column and a potential answer, which is a column that has some of the same values in it, right? And now I need a metric of which column is better than another column, right? So in the, this is the outline of the tool. So I have a set of tables in the data lake. I'm going to do some pre-processing to extract sets from that table, from the tables. And those sets are just the attributes, right? And then I'm going to do indexing. And so I'm going to have this search index that allows me to do this joinable table search at interactive speeds over millions of tables. And so I have a query table, and the user gives me a query set, just a single column, and I go over this search index, and I return a column and table IDs of things that actually join with it. All right. And so that demo that I just showed you was a demo that does this, right? It has all of this kind of encapsulated in it, where I gave you a column, the user took a column, and I pulled up things that actually join with it. And so I'm going to go over two techniques that we developed. One is LSH Ensemble, which was we used for the demo. And the second is Josie, and I'll tell you how they differ, and that was just published in Sigmod this year. So let me start with LSH Ensemble and how we do this. And so this is work by Eric Zhu, my PhD student, and he's very proud of his GitHub. It has a lot of stars, so he makes me show this slide. So it's a threshold-based search index. He has in there a whole bunch of data sketches in a Python library, including Minhas LSH, and it's been used by a number of groups out there. Now, how do we measure goodness? How do I tell if one table is a better join candidate than another? So I need a metric for doing that. And so I have my query Q, and I have X. X is a potential column that joins with it. Now, do you guys know J-card? The J-card measure is up here. The J-card measure is the size of the intersection divided by the size of the union, right? And it's a very popular measure in similarity search. It's used quite a bit.
These are just the sets of values for the two attributes?
Yes, this is the sets of values, right. So I've extracted the sets and gotten rid of duplicates, yeah, which is and we'll come back to that point later on. And so here, if I have Q and X that are the same size, and they have this overlap, and I have Q and X prime that have the same overlap, the size of the dark blue and the dark yellow is the same, but X prime happens to be larger, then the J card for the blue guy is much greater than the J card for the yellow guy, right? And that's because I have Q union X in the denominator, okay? And so I'm going to claim this is bad, because and this is kind of known to be bad because it means J card is biased to small sets. So if these two sets have the same overlap, the same number of things that overlap, but X is smaller than X prime, and so I'm going to return X. And my index, if I use this, is never going to return X prime. Or X prime is going to be really far down in the list, just because of the size.
And so X prime could be a universe of objects
Yes.
that contains everything, and you might be interested in
Yes.
joining.
Exactly. Yeah.
I have an example. I mean, you have the students of one department
Yeah.
taking exams, and the students of the whole university,
Yes.
which is a very reliable data set, but
Yeah.
then it's much bigger,
Right.
and you never join. Whereas the actual information on the students is the university register.
Yeah, exactly. And so you want to find that, right? Because that has all the students that you have, and so it's a very valuable join candidate. Exactly. So I don't like JCard. I'm not going to use JCard for exactly that reason. So instead, I'm going to use containment. And the containment is the size of the intersection divided by Q. And so, and you can think of it as just a normalized version of the overlap. So in this case, the containment is going to be the same, independent of the size of X and X prime, right? So if for example, if X and X prime contain all my values, I want them both to be returned, and they're equally as good, right? All right. So I'm going to claim that containment is much better for the joinability search problem than JCard. And because if it has more joinable rows, I want the more joinable rows than the less joinable rows. And my search now, I'm going to define this as a threshold search problem. And that means I give you a threshold for the containment score. And I find all the tables with a containment score over that threshold T star. And so if I give you a threshold of 90%, that means I want all the tables that have at least 90% of the values in my query table. If I give you 100%, then I say I want only tables that have every single value that is in my join column. And so my user is going to specify how much error they permit, which you can think of if after you do the search, you do an inner join, it's kind of the number of tuples that are left out of the inner join, right? All right, so we're going to use min-hash LSH. So min-hash is a technique from Andrew Broder back from 1997. It's an old technique. How many people have seen min-hash or LSH? Yeah, a fair number of people. Okay, it's a classic database problem, database solution. And Andrew Broder did it for documents. He used min-hash for judging the similarity between documents. So for him, the sets were 2 documents, right? But I'm going to use it here for joinability, where the sets are 2 attributes. And so the idea in min-hash, I have a set X and a set Y. And I'm going to hash the set X, and I'm going to take the minimum value of that hash, say some F0, over each of the X values, right? So, and I'm going to do the same for Y. So I have some hash function. I hash every value in the set, and I take the whatever minimum value I got, and then I do the same for y, and find the minimum value that I got, right? And it turns out what Broder showed was that the probability that my two H0s are equal to each other is equal to the J card. And so I've gone back to J card here. And to get the intuition, think of the extreme cases. So if x equals y, if they're exactly the same set, then of course the minimum value is going to be equal, right? So the probability that they're equal is 1, and also the J card is 1, because they are identical sets. If x and y are non-overlapping, right, so then the J card is 0, and the probability that the min value is the same is 0 if I have a good hash function, right? Because they're distinct, so they shouldn't be hashing the same thing, right? So that's kind of the intuition. And so that's the min hash. And in min hash LSH, what I do is I do these hashing k times. And I pick a k, and I do it k times, and then if I do it k times, it turns out that the J card is approximately equal to the number of times the hash values for two sets are equal. Okay, so I hash x into k buckets, I hash y into another k buckets, and then I check how many times they're equal. And the number of times they're equal is approximately equal to the J card. And this was Andre Broder's result. And so the beauty of this is that I can build an index. I can generate k such hash functions and insert the sets into k respective hash tables. And a query then, all I have to do is at query time, I kind of check the overlap in these hash functions. All right. Now, what I've done is take a massive set, and so I remember these sets could have millions of values in them, and I've hashed them down into k-size signature. So I've taken all these sets, the big and small sets, and they all have now this k-size signature. But the signature has this really nice property that I can use it to approximate the J card between the two sets. Okay, and okay, the problem here is I've spent some time telling you I don't like J card, and this works just for J card. Yeah, you had a.
Yeah, that was my question.
Yes. Okay.
Yeah, you are using that min hash with the union, yes?
Yes.
With the union.
Yes. Yeah.
With the measure that you didn't really.
Yes, I haven't solved that problem yet. Yeah, and so this has been used for document search, and it's been used for things like plagiarism detection and stuff where this bias towards small sets is appropriate, right? So two documents are probably more similar if they're of a similar size, right? So for Andre Broder's problem, J card is a fine measure. For mine, it's not. So, okay. So, now, the reason that min-hash LSH doesn't work for containment is that containment is an asymmetric measure. And min-hash LSH has been shown, it works well with J card, which is symmetric, meaning the J card of XY is the same as the J card of YX, right? But containment is not symmetric, okay? And min-hash LSH, it works with other symmetric measures like cosine, lots of other measures, but it doesn't work with asymmetric measures. So Eric was pondering this, and he found this lovely paper by these statisticians that said, okay, we're going to create a min-hash for asymmetric measures, including containment. And so this was a paper that existed when we started this. And the way they do this is they take, if you have sets of different size, you find the largest set, and you pad the other sets with completely new values that are not in your vocabulary. So they're brand new values that you're not interested in, and you pad all the sets to be of the same size. And then if you do this, padding, then the containment is monotonic with respect to J-card on the padded values. What that means, being monotonic means that now I can use my index to find things based on J-card, and the highest things I find will have the highest containment score because of this monotonicity. So I can use my index in this. So we said, okay, then we're going to use this index from our joint search. Everything's fine and good. It works horribly on open data. And the reason is the skew in the size distribution in open data. So remember, the largest set, it can be 22 million in our sample. That's a lot bigger than the smallest set, which is 1, right? The smallest, and even if you get rid of the tail and say the smallest set is 10, it's still, the difference is much too big. And so if you do this on real data that has the skew distribution, you find that the sketches contain mostly these padded values. And so you get really bad recall with this because you're being skewed by these padded values.
Whereas it works well for web tables and for enterprise data, I mean,
It-
the other two classes that you showed.
It works, even for web tables have enough of a skew that it didn't work well there. It works well in, Srivastava and Lee showed that it works well for document search and for plagiarism detection, I think was there, where the difference between the smallest and the largest was much less than the actual set sizes. Yeah. Right, so I've made this argument. It doesn't work well because of that. So we couldn't use the asymmetric. So what we decided to do was instead use a partitioning scheme where we would partition the data up by size. So you have one partition for the smallest data, you pick some the number of partitions, and the last partition was for the biggest data, okay? So we're partitioning things and reducing the size of the problem. And then we were using a transformation of containment to J-card based on, that uses the upper bound of the partition in the actual transformation. And what Eric showed in his thesis was that he could come up with an optimal partitioning for any data set distribution. And in addition, if the data set size distribution was Zipfian, then the optimal partitioning strategy was kind of an equi-depth one. And this is a little bit counterintuitive. For example, if you actually had uniform data where the size distribution was uniformly distributed, then the optimal partitioning wouldn't be equi-depth. It would be something that was kind of very skewed to the, I believe, to the largest data sets would get most of the partitioning space rather than the smaller ones. But he gave a kind of a closed form for the optimal partitioning where that minimizes the number of false positives that you get with the index. So here's what he showed in practice. So I have up here min-hash LSH, which is just the J-card version, then the asymmetric version, and then LSH ensemble with different numbers of partitions, 8, 16, and 32. And what you find is that the asymmetric one, the precision of the asymmetric one is fabulous, is kind of the best, but the recall is really low because of that padding. Whereas LSH ensemble is able to get almost as good precision and really high recall, depending on the cell. And the query performance, the min-hash LSH, the LSH ensemble gets better query performance in part due to the partitioning, but also due to having fewer false positives due to the higher precision in it. Because a false positive is something that you just have to throw away later, and it decreases query size. So we're claiming, so our mean query size at 32 is about 3 seconds. And we're claiming we're getting near interactive speeds, right? And you can certainly speed this up with hardware solutions and things like that. This is on one machine query performance. And I believe that's over the 50 million tables average query speed. So that's LSH Ensemble. And since LSH Ensemble, there was a technique called Lazo that was published in ICDE this year that follows up on LSH Ensemble, and it's from some people from MIT. I think Sam Madden is the prof on that. And what they did was they said, wait, min hash is one way of doing this, but there's this new thing called one permutation hashing. And basically, the difference between min hash and one permutation hashing is what we're doing this hashing k times, and they're doing it once, one hashing. And they showed that the accuracy of this and I believe they showed it for JCard though, is they can get close to min hash accuracy. And it's computationally much more efficient. So where that makes a difference is in building the index, not in query time. And in the previous slide, I showed you the query time. So our times for building this index are hours. It does take quite a while to build our index. So Lazo is an LSH index that uses this one permutation hashing for both containment and JCard. And in particular, they're using that enterprise data lake from MIT. So in that one, the differences in sizes, they're claiming that JCard is still relevant for that data set. So, but they do both containment and JCard. And so their contribution is a computational efficiency in index building, and better accuracy at higher thresholds. When your threshold is 0.9 or above that, they're claiming better accuracy. And this is part of my challenge. So I will be doing challenge problems. And this is one possible challenge problem if you're interested in it, to kind of explain how one permutation hashing can get higher accuracy than min hash. And there's lots of other related work. So in this, let me start over on the right. In kind of mass collaboration search, this is the web table search. There's lots of other techniques for finding related tables, and most of it uses metadata. So there's the work by InfoGather that I mentioned before that uses, you give it a column like CEO, and it finds tables that have the CEO information in it. And so most of the techniques work on web tables or linked open data, and they use either just metadata or metadata in combination with data. But the problem, as I outlined it, is closer to set similarity search. And there's a huge body of literature on set similarity search. And some of it uses JCard, but some of it uses containment. So there are techniques for doing finding similar sets based on containment. And the reason we didn't use this work is because this work looks at massive sets of things, but the sets themselves tend to be small. So this work mostly is looking at things like the Enron emails. So each set is an email, and the maximum size of the set is 3,000 values in it. or the AOL data or DBLP, and the maximum set sizes are relatively small there. And also the dictionary sizes, the vocabulary is relatively small in comparison to open data and the set sizes. So we kind of thought that there's no way, one difference in this work is that this computes things exactly. So my techniques is approximate, right? I'm taking these massive sets and I'm hashing it down into these sketches, and then I'm approximating the containment score, right? These techniques are exact, and they can find all the things, all the sets for a certain threshold, and so forth. And yes.
Dictionary size is the size of the ensemble of all possible values that can be found in the
Correct.
dataset?
Correct. Yeah. And for what I've done in terms of the approach that I've described so far, dictionary size doesn't matter, right? But I'm going to go on to another approach where the size of the dictionary is going to matter in a second. Any other questions? All right. So when we saw this, we thought there's no way we can do an exact approach on data lakes. The sizes are just too different. But in Sigma this year, we actually studied it a bit more, and we created what we call JOSI, which is an exact approach for computing containment over data lakes. So, JOSI versus LSH ensemble. So they're different. So LSH ensemble is approximate, and it's a threshold. So I give you a threshold 0.9% or whatever it is, and I find every set that has a threshold above 0.9, at least approximately, right? JOSI is exact, and it's going to be top K. So I'm going to give you a K, I want 10 tables back, and I find the best 10 tables, right? All right. So, so top K versus containment. So, in the nearest neighbor literature, there's always a debate on this, on whether or not users can understand thresholds. Because if I say 0.9, set a threshold of 0.9, I may get nothing back, and I may get millions of tables back, right? And so, setting the threshold is kind of an art. So people have said instead what humans like better is top K. They can tell you how many things they can handle conceptually, and so it's a better way of setting it. And so there's no knowledge of the relevance is needed. And importantly in this work, kind of surprisingly, we showed for small k, we can actually do the exact computation faster than the approximate computation. And everybody's familiar with top K when you have a kind of a web search. And the web search, you just, only the best 10 things are displayed on the page. Yeah. So, top K overlap set similarity search. So we're going to use, in this work, overlap. I just got rid of the denominator. So I'm going to use the absolute value instead of the normalized value, but it's really the same thing as containment. Now, here is why the vocabulary starts to matter. So all these approaches that do exact set similarity computation use inverted indices. And an inverted index is an index where for each possible value in the entire vocabulary that you have, here I have just a query, but the index has for every possible value in the data lake, I have what's called a posting list. And the posting list contains the IDs of the sets that contain that value. And so here on the posting list for V1 has X2, X3, and X4 in it. And the same for V2, but the posting list for V3 has X1, X2, and X3 in it. All right. And so for each value, I have these posting lists. These are all the sets that contain that value. And that's a standard inverted index. And so the vocabulary size starts to matter because in traditional inverted indices, they were built, let me go back to, all of these techniques use inverted indices, but they're using them for dictionary sizes, and in this case it's very small, but like 4 million. If I'm going to scale that up to 500 million, the index itself, like paging and all this stuff on the index, starts to matter. So I'm really pushing the limits on an inverted index when I have a vocabulary size that big. Where did I go? In explaining this work, I just saw there's 5 minutes left. I probably can't explain this in 5 minutes. Should I stop here and take a coffee break? Are there any questions? Any questions that came up over the break? Oh. All right, so I'm going to tell you how to do set containment with an inverted index. So recall our setting now that is for every value in the vocabulary, we have a set of posting lists. So the posting lists are these things vertical. And then you also have the sets themselves. So X only contains V3 and X2 contains 6 different values and so forth. And so in order to do set containment, or actually you could do JCARD, you could do other things using this method. The traditional method for doing this that's in like the IR textbooks and so forth is what I'll call posting list union. So I have a query, and my query here has 4 values. And so I read all of the posting lists for the query. So in this case, I read 4 posting lists, and then I count up the number of times each set appears. And so the X4 appears 4 times, X3 only once, and X2 twice, right? And that's exactly the containment. So the containment for X4 is 4 values, and the query only has 4 values, and so that's my top 1. And so the cost of doing that on this particular data set was essentially I had to read 4 posting lists containing 7 values total, and I can compute the top 1 for this simple example. Now, another technique that has been proposed for this, if I read a posting list, then I can read a set that's actually in that posting list. And once I've read that set, I can compute the overlap between Q and that set. And so if I do that for all the values in the first posting list, I can compute the overlap with X2, X3, and X4. And if I do it that way, oops, sorry. This is a technique that's called prefix filtering, and it was introduced by Sergey and some other folks from Microsoft. In this particular example, I don't get a win because I read 1 posting list and then I'm reading 3 different sets. I'm still computing the top 1. I'm still getting, because X4 has the highest overlap. So I'm getting the top 1 answer, but I'm reading 18 different values. So these are the 2 main techniques in the literature. The first one just reads all the posting lists. The second one reads a single posting list and then reads the sets in that posting list, and it keeps a running tally of the top K. If I'm doing top 1, it just keeps the first one. But by keeping a running tally of the current top K, you can actually do some pruning. And that's what the prefix filter paper actually showed. And so in this example, for this data, the plain old read all the posting list is the better approach. But if I change the data, and here the query is the same, but the data changed. So if I do read the for posting list, it just so happens those posting lists have more values in them now. So I'm reading 13 different values. And I'm getting the top one, which is X4. In the prefix filter, I read this posting list, and then I only have to read 2 different sets. And when I read X4, I know it's the top one, and I'm done. And in this case, because I've read the sets, and I have this running tally of sets, I've actually only read 7 values, and the prefix filter is better. So when we approached this problem, these were the 2 kind of best techniques. There's some other kind of nuances for other small ways of pruning them, but they were basically the best techniques for doing this. And what we see is that the cost is going to matter if we're trying to do this over a data lake. And we have data sets with these different kind of distributions. So the bottom 3 are the data sets that were used in the prefix filter paper and other set similarity papers for evaluation. And then we have our 2 big data lakes at the top. The basic principle here, though, is that reading a set eliminates posting lists that you have to read. So if I read V2, and once I read X4, I know that it overlaps with 4 values here, and so it's top one. So I don't need to read the rest of the posting list, okay? So that's one principle that was introduced by the prefix filter. That's M&A, sorry. And, right, so the maximum overlap of any unseen candidates in the posting list is, there's 3 values remaining, and 3 is less than the current highest overlap, which is 4. So I know my search is done. And reading posting list also eliminates sets, which is the other principle. So if I read this posting list and I read this posting list, and assume the current top one has 4 overlaps with it. So then by reading these 2 posting lists, I know that X1, X2, and X3 only have 1 more value in them, so they can't possibly be in the top 1, right? And so by reading these 2 posting lists, I don't need to read the first 3 sets, period, right? So I eliminate reading this region of the sets. And so, given those 2 principles, what we decided to do was kind of combine this. And previously, the approaches were just read all the posting lists, or alternate, read a posting list, read the sets, read a posting list, read the sets. So we said, well, why can't we look at the actual data distributions and try to estimate which approach is going to be better at each step? And so then we had an approach that kind of measures the work that you're going to need to do as a total of the read costs of the remaining posting lists and candidate sets that you might have to read. So we measure progress as a reduction of this work that you have to do. So reading a posting list reveals intersecting values, and those intersecting values reduce the work in reading candidates. It tells us certain candidate sets can't possibly be in the top K. Reading a candidate set, reading across, improves the prefix filter. It improves the current top K that you have, and that can reduce work in reading posting lists. So, and so we measure the price as the read costs associated with this progress going forward. And so essentially we have this loop. We estimate the progress, and we choose to read the posting list or candidate sets that maximize this progress minus the price of reading them, because we can estimate how many things have to be read in a set versus a posting list. So in this, so I don't have the actual equations here, but you can kind of understand how this goes for a given set of values. What we found on open data and web tables, so on the left we have open data and then web tables. We compared with this list union approach, which was always read the posting list, versus prefix filter, which alternates, reads posting list, reads sets, and Josie, which has this cost-based notion of deciding which one to do. And so Josie is in the green, and we found that for, this is k equals 5, k equals 10, and k equals 20. And these are small queries, medium-sized queries, and larger queries. So on small queries, and this is queries where the query itself has less than 1,000 values in it, the Josie is always doing better than the other two. And for these small queries, the list union is pretty good, right? So if you have a small query, just reading those lists, that a few set of lists is all right, right? But once the query gets larger, the list union gets worse, and Josie can stay low. And for larger queries, there's even a bigger gap there. And the trade-off is a little bit different in web tables. So in web tables are smaller, meaning the sets are smaller, and also the number of posting lists is smaller. But here we have the same query set size going across. And still, the other techniques actually do better on web tables because they're smaller sets. But Josie is still able to outperform them by kind of adapting to the distribution of the data itself in these. And then, interestingly, we compared against our approximate technique. And we showed that in query performance, and this surprised us, the exact technique for small queries and small k actually does better, can outperform them. And so in order to compare these, remember LSH Ensemble is a threshold-based technique. It's not a top K. And so LSH Ensemble 60 is a technique that sets the threshold at 60. And if it gets the top K in that, then we're done. But if it doesn't, we incrementally lower it. And LSH Ensemble 90 starts with a threshold of 90 and then lowers it until the top K. And so here, Josie again is the green one. And so this is K equals 5. So I only want a small number of things and a small query size. Yeah.
So just for experimental setups, is it like single-threaded? Is it distributed? Is it?
Yeah.
Because it matters somehow.
It does matter. So this is single-threaded. So we weren't making use of LSH Ensemble would improve if we had distributed it across different threads or cores. So this is all single-threaded. That's right. So that's right. Yeah, we could have improved the performance of this. So yes, yes.
Will not improve as we scale up.
That's right. Yeah, I don't know the state of the art on distributed inverted indices. It's probably, yeah.
For parallelization.
Yeah. So we haven't exploited any of that. This is all single. So for K equals 5 and small queries, where the performance is much better. And that continues all the way up until you get to about query sizes of 2,500 or so. Above that, then LSH Ensemble is doing better. So when the query sizes get large, and also when K is more than 20, you need approximate techniques as well. So, but yeah, modulo what you can do with parallelization, yeah.
Continuing on the experimental setup, how large are these indices? Can they fit in a decently sized memory?
That's a good question. No. Were they all in? That's a. no, we were doing some paging of them, and I don't remember the exact size of the indices. Yeah, so for this is open data, and yeah, so this is the number of posting lists, but yeah, I don't have the size in gigabytes. Sorry, I think it's in the paper, but yeah, yeah. Other questions? Yeah. Okay. Oops, wrong button. All right, so future work. So that's kind of where we stand. So this is Josie, which was SIGMOD this year. So this is state of the art. There's lots more work that can be done here, right? So we have this kind of architecture where we do pre-processing, we extract these sets. And this is true in both the approximate techniques where we're using LSH hash indices here, as well as for the exact techniques, we have to build this massive inverted index. Both of the techniques allow new sets to be registered because it could grow the vocabulary size. You have to be a little bit careful in how you do that with the inverted index, because I didn't cover a few of the nuances, but it does require having a total order over the vocabulary values, an order that you have to know in order to get all the optimizations in there. So then we do this indexing, and we create the search index, and we have a query table, and we get out our results. There's lots of other things that we could do here. One fascinating thing is multi-sets, which I think is important because we're database people. We know that the size of the join isn't exactly the size of the overlap of the sets, right? So if I'm finding top K or threshold, the best overlaps in terms of set size. If I have a data set that's all about Europe and it has a few countries outside of Europe, if I cover all the countries outside of Europe and I don't cover Europe, and Europe is repeated most often in my data set, that's going to be unsatisfying to a data scientist, right? So the multiplicities, the number of times something occurs, does matter, and it matters in the join. So it would be way better to, hit the correct button, sorry. To be able to do multi-sets and to have a measure based on multi-set overlap, right? Other things you can do, it would be interesting to be able to do this based on entities as well, right? So if you can find a way of mapping values into entities, can I do that? Can I find some approximate way of doing join search? So all my techniques are exact value match, right? We have very good techniques for doing fuzzy joins, right? There's a whole literature on fuzzy joins. And fuzzy joins take two tables, and you take the columns, and so a lot of the techniques break the values down into Q-grams, into smaller snippets. And then they do, guess what? Set containment on those snippets, right? And so some of the techniques that I surveyed for doing set containment are exactly for fuzzy join. But it works on two tables, and it's not going to work. Just a straightforward implementation of that is not going to work for the search problem, because you're losing too much information by breaking all these strings down into Q-grams, and if I just search by Q-grams, I'm going to get junk back, I think. That's a hypothesis that should be tested at some point, but I don't think that's going to work. And we have very good techniques also for doing fuzzy join using edit distance, right? There's some good papers on that. I have no idea how to turn that into a search problem. So there's lots of interesting things on how to kind of relax the problem here. Numerical data, so for heaven's sakes, hit the right button, Renee. I don't know how to do numerical data, right? Well, I do, but it's not terribly meaningful, right? If I do this join search on numbers, it's going to give me a lot of false positives, right? It's just going to tell me, oh, we've got two attributes here that have a whole bunch of integers in common, but what does that mean? And how do I do it meaningfully in taking into account precision of numerical numbers and things like that? So new techniques are needed for numbers. Can I do this based on embedding vectors? And I'll have more to say about that when I get to the union as well. And the search index, how do you incorporate these things into a DBMS? A lot of people say that even within large warehouses and so forth, being able to find things that join together, it has become a problem. Data warehouses have become that large. So can I add a search index into a warehouse or DBMS? How do I distribute it? How do I exploit parallelism? There are lots of open questions here. And going back to a question that was asked at the beginning, how do I do search on multiple columns? Yeah, so if the best way to join things together is based on borough and year, I can't do anything. Think about this for a bit. In order to do that, in both of my techniques, I would have to index every pair of columns in both orders, right? That's not going to scale to a data lake, right? Right now I'm indexing millions of columns. I'm certainly not going to be able to index million squared columns. So how do I do that? Is there some way of using single attribute to do pruning and still get back high recall for multiple attributes? It's something I want to be able to do. I think this kind of tool, sometimes joining on multiple columns is exactly the right thing to do. And it's just a completely open problem how to do that. Yeah. Oh, I've forgotten how to use this. There. And there's lots of applications at the front end. Integration with machine learning systems and BI systems and citizen data science and data marketplaces. Actually using this as a back end for feeding some of these applications would be very interesting. But in order to get to any of those applications, I think I need a solution for the multi-column stuff, because if you can only do one column, people get unsatisfied. They immediately want to do more than one column. All right. So that's all I'm going to say about join search. Is there any questions on joins? Or now I'm going to go on to union.
For finding applications based on your survey, are there cases in which you need to join only one column, I guess, or some simple tasks?
Yeah, there are interesting cases where one column is enough, because there are things that are identified that they have an identifier that's a single column. Yeah, so I think exactly. So I think it is useful, but it would be more useful if I could do multiple column. And we've thought about, well, if we're going to do multiple columns, maybe I only need to index things that are keys. Right? So because most of the time, non-key to non-key joins are not that interesting, right? So most of the time, you either want to find a column that's a key in the data lake, or you have a key and then you want to find other things where it's mentioned. So you're finding the foreign key. So there might be some ways of doing that, but then I have to be able to know over a data lake what are the keys. That's not an easy problem. So Felix Neumann is working on techniques like that, but he has a technique called, what is it called, DUCC? DUCC, D-U-C-C, unique column combinations, right? Yeah, thank you. For finding on a single table all the keys, right? And it scales to a massive single table. But we actually tried, you can run it in parallel over 1 million tables. It doesn't quite work. And some of these tables can be really, really wide, and that gets problematic. So lots of interesting open problems. Yeah.
So I have a question. Most of the things
Yeah, huh, recall.
Like at least
Yeah.
all sets like having new embeddings and so on. You basically want to get more things to join with, right?
Yeah, that's true, yeah, okay.
So I was wondering, like, what is your like current state? Like, how maybe just for single columns. Like, is there some, I don't know, some number you can say how much of these tables you already have, or is it impossible to get this number because, like, going through millions of tables to actually understand what the current state-of-the-art recall is might be hard.
So you're kind of asking how many, if I give you a random table in a data lake, how many things does it join with? Right? Is that what you're asking? Yeah.
Like, if I give you a table and you would basically give me all possible joinable tables,
Yeah.
with your method, how much would I get? Like,
Oh, yeah. So actually, you get quite a lot. So I think in those experiments, he divided the queries into small, medium, and large, but he basically took random tables from the data lake, and they did join with a lot of things. Is that your question? Or is your question like a random table, maybe most tables don't join with anything?
I mean, maybe the other part of the question is, so if the recall is already pretty amazing,
Yeah.
should we focus more research on like making the recall better, or should we focus more on making it faster? Or
So the recall is very good, and in the exact techniques, I'm getting everything. So my recall is 100%. But I think your question is, if a table doesn't join with anything, then the recall is 0. So of course you can find that fast. Is that?
I mean, I think it's a question of definition. Of course, like if you say exact,
Yeah.
but then you will not find anything. But maybe you don't want this definition. Maybe you want some.
Okay, I see what you're saying.
Right?
Yeah. So you're kind of asking me if using my containment and the exact measure, if a table would join with 5 things, is there some way of knowing how many things it would join with if I relax that somehow, that it should join with, right?
And some person would say, yeah,
That would join.
kind of makes sense to join it.
Yeah, I have no idea what that number is. Yeah, because, yeah, I don't know how we'd go about doing a study of that. Yeah, I mean, because there could potentially be something like I could have an English and a French table in there, right? And in which case, none of my techniques are going to work. But somebody would say, "Oh, you should have returned this French table because it's exactly about the same thing, right?" So yeah, I don't know how to do that study. But your other question was kind of interesting. Even in terms of containment, I guess we could go through and say how many columns are there, at least one other table that has a containment of this in it. Our intuition from that, at the very beginning of my talk, I gave that cloud where we took a random table and joined it. My intuition is that things do join quite a bit. This could be interesting to study because something that I didn't cover. There's a lot of duplicates and there's a lot of versions of different things. So, and the way I define join search, my best answer is the table itself, right? And so that could be misleading. Yeah. So that might be interesting to study. How many tables are there out there that join with it that aren't the table itself, that have some notion of new information? Yeah.
I was wondering, how do you deal with like sparsity? Like basically you don't have like 100% join, so you don't have all of those values in web tables or open data. So basically, how dense or sparse your enriched data is in practice?
Oh yeah, because if I am joining two tables that aren't 100% contained, then I would probably use an outer join, and I would get a sparse table. Is that kind of what you're saying?
Yes.
Yeah. We haven't done anything with that problem. But yeah, we haven't looked at that. Yeah. All right. So now I'm going to talk about union. So we have a query table, and we have candidate tables, just similar to the join problem. And we want to understand when a candidate table can be unioned with a query table. So some attributes might overlap, and if they overlap enough, first you have to define enough, but if they overlap enough, you might say that they're unionable. Some attributes might have the same kind of information, but of the different entities of the common type, sorry. So here, if I had some kind of ontology or knowledge base, if I know that these are all regions in the state of Washington, these are regions in London, then I might say that these are unionable because they're both regions of a similar size. And some may overlap because they use semantically similar words. So here, there's no actual words in common, but gas and gasoline, we know, are synonyms. And railway diesel has something to do with fuel, oil, and they seem like semantically they're describing something similar, right? So these are three different types of overlap, and I'm going to try to formalize them and then turn it into a search problem. So I have a query table and a candidate table, and I want to find out if an attribute or multiple attributes are unionable. So I'm going to take the query table and I'm going to look at different attributes that might actually overlap with it. And then I'm going to use that to pull out these candidate tables out of the search. So what we defined here was a probabilistic model. And our model is the likelihood that two attributes, viewed as sets again, are samples drawn from the same domain, okay? And we're going to have three different types of attributes: set, semantic, and natural language. And so for the set domain, we view the two attributes as samples from some common domain. And if you view them as samples from that domain, you know that the overlap in the set domain follows a geometric distribution. So using that, you can, from the measure of the overlap, how many values overlap, you can define a likelihood that they actually came from the same domain. We can do the same thing with semantic things, but we view them as entities and we map those entities up into an ontology. And we're going to use Yago because it's an open ontology and that has relatively good coverage on things. So we're going to map the values up into the ontology and then view them as entities, and then do the same thing we did with actual values. We take the overlap in the classes they map to, and judge the likelihood of those being drawn from the same domain. Now, for natural language ones, we're going to do something different, and we're going to actually use word embeddings. So we are going to take pre-trained word embeddings. Do you guys know what word embeddings are? So a word embedding takes every word in natural language, like gasoline, and it maps it into some vector of some dimension. And the idea behind this mapping is that two words that are semantically close to each other should map to vectors that are close to each other. And it's a technique in machine learning that has turned out to be incredibly powerful for reasons a lot of people don't understand. It's one of the, am I wrong?
Goes outside.
Yeah, is that the ghost of some ML person who just maligned our technique? It does seem to work really, really well, and actually it worked really well for us as well. So the attribute unionability for set and semantics, we're going to postulate D is a set of values or a set of entities from ontology classes, and we're going to measure the likelihood, given the overlap between A and B, the likelihood that they're drawn from the same domain. Okay. And then from natural language, we're going to convert the values to word embeddings. And so for each value, we convert it to a word embedding, and then for the column, we sum up those word embeddings. And then for 2 columns, we measure how close those summed up word embeddings are. And we use that to measure the likelihood that they're from the same domain. And then we have this notion of ensemble unionability. So for ensemble unionability, so we have these 3 different measures, but we don't know for any pair of attributes, we don't know which of the 3 measures to use, right? And so what we do is we apply all 3 measures, but we can't compare them. So the fact that set unionability might be, say, 0.4, as it is over here, and the natural language unionability might also be 0.4. It doesn't mean they're equivalent to each other. They're not comparable to each other, right? And so to make them comparable, we compute the cumulative probability distribution of all the unionabilities in the data lake. Okay, suspend disbelief on this for a moment, where we just take all pairs of attributes in the data lake and we compute this distribution of how close they are. And then we take a particular pair and say, well, that 0.4 actually is very high in this distribution, so that's very unlikely. And that means it's a strong signal that these 2 things are unionable. Whereas over here on the natural language, we're actually only just a little bit above the halfway point. So those are less likely to be unionable in comparison to all the different things in the data lake. Okay. So there was a big scalability issue with what I just said, right? So we, first of all, in order to compute this cumulative distribution, and then there's also a scalability issue with just being able to compute the 3 raw unionability scores. So I have to solve both of those problems. And I'm apparently not solving it on this slide, but hold that thought. I think I solve it on the next slide. The other problem I have is I want for a query table to be able to compare if I take this table and I union it on 1 attribute versus I union it on, say, 7 attributes, which is a better alignment. And so that entails that I can compare unionability on 1 attribute or n attributes with m attributes, where those are different numbers of attributes. I animated this, 1 set versus another set. So in order to do kind of all of this, first we noticed that set and semantic unionability is highly correlated with the J-card score. So we're going to cheat, and we're going to use an LSH, min-hash LSH index for J-card, so back to what it was originally designed for. And notice that the J-card, things with really high J-card have high set unionability. And it's the things at the top we really care about, right? The things that are really unionable. And so we're going to use these J-card min-hash LSH indices to estimate the set and semantic unionability. And similarly, we found that the natural language unionability was correlated with the cosine of the topic vectors. And cosine happens to be a symmetric measure that you can put into a min-hash LSH as well. And so we have a cosine version of it to compute natural language. And so that means we can use these LSH indices to efficiently retrieve candidate attributes, one at a time, for set, for natural language, for the other. And also, did I take it off the slide? No. Maybe I didn't. I'm missing a slide. So in addition, yeah, go ahead.
Something in the previous slide, when you were saying that two measures are not comparable in the previous.
Yeah.
Yeah. So here, one thing is whether you compare the values between the two measures. The other question is, if they give you, let's forget the two, let's take one, and they tell you 0.8.
Yeah.
Do you know if 0.8 is high or not? Is it also a problem?
Yeah.
Do you know that 0.8 is high?
Yes, that's a problem. Yeah, and so the way I'm going to solve that, so yeah, here are my example. Wrong button, Renee. Yeah, it was 0.4. Yeah, so imagine it's 0.8. And so the way I'm going to say, I'm going to look at the probability distribution, and say, well, actually, there's very few things that are above 0.8 because 0.8 is right here. And so that is unlikely and high, yeah. And whereas 0.4, almost half, a little less than half are above that, so that's not as good. And so now I am missing a slide, I apologize. To compute this, I'm actually going to use my LSH indices as well. So I put all the attributes into these LSH indices, and I can use that to estimate this the cumulative probability distribution here. And then I can use the index itself to pull out the likelihood of something of a particular score being rare or common.
This is like a calibration when you turn numbers into probability.
Yeah, we're turning, yes, yeah, right, in comparison to the, yes, that's what we're doing, yeah. Okay. Okay, and we did this, okay. So evaluation of table union on open data. So this is our open data lake. And what we found was that the natural language unionability outperformed set and semantic individually. And by outperform, let's see, where is it? It's purple, the natural language one. So it gave a higher precision and a higher recall than the other two individually. Let me back up and tell you how I measured precision and recall. So that's not obvious, right? So in order to have accuracy for this, I had to have a corpus on which I know the exact right answer. I know what's unionable and what's not, right? So in order to build that, so I couldn't just do this randomly on the data lake because I don't know what's unionable there. So we took a bunch of the biggest tables from the open data, and we ran a process on them where we randomly picked a subset of the attributes and a subset of the tuples and created new data sets. So these new data sets were projections and selections on the old ones. And we created a whole bunch of them. And we started with massive tables that were distinct. So our assumption was the original tables we started with were not unionable, and the random subsets that we generated from it, when we generated thousands of different subsets, were unionable. And so that's how we got the precision and recall. So that's on, this is, and we made this a corpus public because we called it a benchmark because we know exactly what's unionable and what's not for people to look at. So in this, we found that this natural language, this mysterious ML technique actually works really well. It has very high precision. But the ensemble uniability. And ensemble uniability was where we turned each of the three into a likelihood and then picked the one that was best out of the three. Actually does perform better. And so that indicates that there are attributes in the data lake that just by means of overlap or mapping up into an ontology, that gives you a better signal than natural language. But if you can only use one, natural language is the best signal for doing the uniability. Yeah. And for the semantic uniability, we used Yago because it's an open ontology. And we actually found that the semantic one had the lowest precision and recall. And we think that's mainly because Yago doesn't have complete coverage over the open data. So it is providing some value. So if you did ensemble without it, you'd get a lower score. So when values actually are from some domain that's in Yago, it provides value. But the open data itself, Yago didn't have tremendously high coverage over. Yeah.
What about training entity embeddings as well?
Ah, yes. So we use fast text. We use pre-trained entity word embeddings for this, for the natural language one. And I had this debate with my students. And I said, shouldn't we train our own? Can't we train our own on the open data corpus? And won't we get better recall? And Eric, my student, said, no, you'd get worse recall if you trained it yourself, because what you want to use is the fast text is trained on what? Wikipedia? Wikidata? Wikipedia, the Wikipedia pages, right? It's not trained on data. It's trained on on text. And he said that the semantics that you want to pull out is from natural language, not from the data itself. So he postulated, maybe he was just trying to graduate, that he didn't have to train his own entity embeddings, word embeddings. I don't know. What do you guys think? Do you buy his argument? But there are people, actually, the MIT guys have their Seeping Semantics paper, which was ICD, where was it this year? They were trying to train word embeddings on columns and tuples in data. Yeah.
So my question was on training. So removing the open ontology aspects. Like you also train embeddings for, like, if you can represent these concepts as nodes in a graph, for instance, and then you train these as. Oh,
okay. Yeah, we could do that. So getting rid, because right now what we're doing is a little bit brittle, because we're doing kind of a fuzzy match of the value up into the ontology, which is it's a little bit brittle, and so.
That can give better coverage.
Yeah, well, I'm not sure that solves the coverage of the ontology, because but it might give a better mapping up into the ontology. So in that sense, it might cover more things. Yeah, so maybe it would. Yeah.
Another related question. So you needed to make a choice when you hack the whole set of text into an embedding, into the numbers, because word embeddings give you an embedding for each word, right? And you have several, a sentence or several words. You need to combine them somehow.
Yes.
Right? And if you take the average or the sum, there might be several options there.
Yeah.
Something that you also had some experiments with. Like sum is better than.
No, we didn't. And so Fatima, she quoted a paper from the ML literature saying that the best way for a set of values was to sum them up. So she quoted something from the literature, and we didn't actually experiment with that. So that could be another way we're losing some signal. Yeah. I forget, I'd have to look at the paper exactly what she cited, but it was for some kind of document thing where they were summing things up and had experimented, but yeah.
You need to make some choice. But I was just
Yeah.
wondering whether you had some experimental comparisons between different ways of aggregating or embedding into one.
No, that we didn't do that. I guess Fatima wanted to graduate. But, yeah.
Actually, there's a paper which says it's a very hard to read baseline. Like the simple averaging of word vectors in a sentence is actually.
Okay, that sounds like what she told me. Yes, so there's a paper that says it's hard to beat just summing them
It's
up.
a hard to read baseline.
With the, okay.
It's still a baseline, but it's very hard to read.
Oh, okay. Yeah. So, yeah, and I'm not sure what the, yeah. So people have said, well, there are graph embeddings, there are word embeddings, there are document embeddings. Why shouldn't there be table embeddings for, and I'm not really sure we know what a table embedding is and exactly what we should be capturing in a table. Because just doing it for columns and rows doesn't seem like it's satisfying, right? So yeah, there's an open challenge problem for you. What does it mean to be a table embedding? So, well, yeah, let me back up. Something that nobody asked me a question. I'll point out. So my probabilistic model is based on testing the likelihood that two samples are drawn from the same domain. But this requires that I know what the domain is, right? That it's drawn from. So nobody asked me about that. But for the set embeddings, we need to know the size of the domain. We don't actually need to know the domain. We're assuming that the domain is the disjoint union of these two, which is something else that is kind of an assumption, right? And you could potentially do better than that if you kind of know, for example, in my example had locations outside around London and locations around Washington State, and so which are completely disjoint, right? And so that is not going to map well going up. But if I know kind of what the domain is that I expect, if I have some semantic knowledge that I want things that are kind of from regions around the UK, and I know the size of that, then I can do better in estimating the likelihood that two sets are drawn from it. So we haven't done anything like that, but there are definitely ways of kind of improving on some of these measures. All right. Yeah, and so search has also been used in mass collaboration data, which is my terminology for any kind of web table or semantic web data. And search there often is done over the metadata. And so there's lots of schema matching techniques where attributes that can be matched are considered to be unionable, right? So if I say that these two things can be matched, then I can union them up. And there's also techniques, Sunita Sarawagi has a technique that uses graphical models that uses schema plus some kind of keyword description of an attribute and tries to learn a model that returns the ranking of attributes. And then the Google folks have done keyword search and clustering of tables. So they do a keyword search, find me all tables about wine. I take all the wine tables, the hundreds of wine tables, and I do some kind of clustering on them in order to figure out what's unionable. And the clustering here again is on the metadata, so it's on the attributes in the data. And there's also entity table work. So a lot of mass collaboration data, web tables, are kind of entity based, and you can kind of find an attribute that's about the name of the entity, right? So the tables are about presidents or companies or countries, right? These tables are about a thing. And so you could also do union based on that assumption, that if two tables are about the same kind of entity, I have two tables about countries, then I can union them up. And then I try to do matching to find which attributes align. Yeah, so we compared our table union on the same benchmark to the Octopus work, which is from Google, which does this keyword search and clustering, and the stitching work. This is from the University of Mannheim, where they use kind of instance-based schema matching, trying to use similarity measures over the values. And we found that with our technique, we get much higher precision and recall. So these techniques work, but not on everything that you're finding out there. All right, open questions and challenges. All right. So, well, are there any questions on union? So, yeah.
General question
Yeah.
or observation. With unions, it is always very difficult. I mean, it is reasonable to have shown how you can detect similarities between some important attributes. But often this open data contains, let's say, statistics.
Yes.
And then you find one numerical figure,
Yeah.
and you don't know the semantics of that numerical figure, and maybe or maybe the numerical figure is the same, but just it happens to be last year and 2 years ago, or things like that. I mean, with the human intervention, in the end you solve these kind of things, but at big data scale, how do you, I mean, one of the concerns I have, especially with the union approach, I mean, with the join is easier because at least the values allow you to correlate things that at least have the same value. With unions, there is always, I mean, I would say that journalists could easily publish the very poor data by making unions of data detected without some sanity check or whatever. I mean, I find these techniques very interesting, but then I always have the concern of how you validate.
Yeah, so my techniques, hidden in them, really work for strings. They don't work for numbers very well. And even the join ones, they'll work for numbers, right? But they might miss a lot of things. If you have things, different precision, you have 10 here and 10.0 here, then I'm not going to be able to join those, right? But you can say, well, you rarely join on numbers, right? So we'll forgive that work. But the union work, yeah, I don't have a good solution for numbers. And you know, notice my example had boroughs and it had gasoline types and stuff, and it had CO2 emission in it, and that was the column I wasn't unioning because, yes. And so my union work really does not work for numbers, and it is a problem because open data has a lot of numbers in it, and it's important to understand those. So the only work that I've seen on numbers, so Gerhard Weikum and Mirek and a few people from his group have some work in web tables, kind of trying to make sense of numbers. And so they're trying to figure out what the units are and what the contexts are for numbers. And I forget exactly when they published that paper. It's a couple of years old. It's something about making sense of quantities is the title. That's really the only work I've seen that does something interesting with numbers. And I agree, it's a real problem. Yeah. Yeah.
You're doing a union between two tables where one has some attributes that the other doesn't.
Yeah.
How do you do for the other one, like the other attributes?
Oh, for the other, yeah. So we can do an outer union when we pull the result back, because you probably don't want to lose those other attributes, and and I suspect if you built a real application on this, you'd want the user to be able to either uncheck some things that you had unioned if they didn't want to union them, or union some additional things. So you'd probably want some kind of flexible interface like that. But yeah.
And for the second table, which doesn't have these attributes remain empty.
Yeah, exactly. Yeah, that's the outer union. I think when the searches get more sophisticated, probably what somebody might want to do is say, oh, is there any table that has these missing values, right? I don't know how to do that yet, but that could be interesting. Yeah. Any other questions? So some open problems. I've mentioned some of these along the way. I think multi-sets or bags are very important in all of this work. Multi-attribute join search, finding tables that join and contain new information, right? So that was the downside, that the table itself is the best answer, right? And so you can think of, and the trick here is to put the contain new information into the search, right? You could always do it as a post-processing step and get rid of the duplicates, get rid of this is just a version of the data set, but I'd like to put it into the search. So can you, for example, say, it should have an attribute whose mutual information with respect to the join column is different than all the attributes I have so far. And can you somehow put that into the search? I don't know how to do that yet, but that would be interesting. Oops, oh, I keep doing that. So incorporating some kind of entity resolution or fuzzy matching or something into scalable search. I don't know how to do that either. Search over quantities with different measures. That's what we were just talking about with Paolo. So how do you make sense of numbers in this? And also schema inference. So the stuff that I've done, I'm only taking into account the values. Sometimes there are, there is schema information, and can you use that? And can you also, you might even view my table union work as schema inference. I'm kind of inferring that these two attributes, even if they don't have headers, are the same, right? Can you do general schema inference over a data lake and kind of create a more semantic representation of the attributes that you have in the data lake? Yes.
So in some way, what in the past today on searching multiple tables at the same time. That is one of the continuum. Also doing from that, where basically the search involves an implicit join. Like you're searching for a person from you used to work in a Toronto University, and that information is something that is not in one table but in two or three.
Right.
But you don't want to join upfront and instantiate all the possible join up. Is it also some search challenge that you use valid or motivated situation?
Yeah, so searching multiple tables. Yeah, I think that would be interesting, and that's that work is more for fact finding, right, and things like that. You're trying to kind of validate certain facts over multiple tables. Yeah, I think that does fall into this, and also kind of generalizing to. Right now, I'm given just a single table, and I tell you, I want things that join with it. I want things that union with it. Can I just give you a table and say, give me everything that aligns with this, or that can be meaningfully integrated with this? And I don't know how to do that. That's a little bit different than what Yanis is doing, but yeah. So you can generalize this search quite a bit. Yeah. And it all comes down to kind of how you're specifying what you want, right? Because he specifies what he wants very differently than I do, right? And kind of that drives a lot of what you can find over these. Yeah.
The idea is that that
Yeah.
apply to several cases. And I think that
Yeah.
this use case is even more relevant to this question because if you have like the schema of an organization, you might have, I don't know, tens or hundreds or more tables. That might be challenging. But here, you really have no, human understanding of the entire space of different schema databases. So just knowing what tables I need to match in order to establish a fact.
Right.
Like a company was supported by related to Trump, for example.
Right.
And this historical connection between Trump or what the company is doing from the fact that he's president.
Right. That's it. I completely agree, and you might need another table in order to make that connection, right? You have to, and all the,
That's right. Really grasp all of these positions of tables that have.
Right. Yeah. No, I like that. Yeah. Yeah.
I'm just asking whether,
Yeah. I think this, So I think what you're saying is some of these techniques might be able to really broaden and generalize that work, right? Yeah.
The motivation here seems to be stronger than the motivation in the enterprise case.
Yeah.
We want to search in the enterprise tables.
Right. Right.
It might be big, but in case of SAP, it might be huge.
Right.
It might not be so big.
Right.
It's really wide.
Yeah, and you can't possibly get your head around everything. Yeah. I completely agree. Yeah. Yes.
So I'm curious, when you, as the number of data grows, so I believe, it's my belief that it's more expensive to do the join. Do your techniques also provide the ability
Oh, I didn't hear the end. The techniques.
I mean, as the number of data grows,
Yeah.
so is the join. Will be more expensive as like the data grows.
Oh, doing the actual join itself?
Yes.
Yes.
That's my understanding. Right?
Yes.
So in your technique, you provide a way to, to improve the joining of the.
Oh no, I haven't done any work on improving the actual join itself, on the join processing, and it does become an issue because especially if you're doing approximate techniques and you're trying to get rid of false positives, you get rid of them by doing the join, right? Yeah, I haven't done any innovation on improving the speed of the join. Lots of other people have. Yeah. Yeah. No. So right now, so the search techniques work on any size. If we're doing approximate search, the larger the sets, the worse the approximation, right? Because I'm using these data sketch techniques. But in like our tool, pulling it back, we're using regular DBMS to do the joins there. So there's no new limit on the size of the join. Did I understand your? It depends on my next student, right? So my students tell me what I'm going to work on. I think there are some very interesting questions in distributing some of these indices and so forth, but I don't currently have a student working on it, so I don't have any concrete plans. Yeah.
some external parameters to the join process with prefix filtering, and then they use estimation to estimate the best parameter, and then the overall join type can be minimized.
Oh, okay. Yeah. Yeah, so I'm sure in this work we can use any of those optimizations for computing these massive joins, yeah.
Yeah. We have the data format heterogeneity, and mostly here we were touching upon the flat data, so tabular data.
Mm-hmm.
So as we have more and more formats, and for example hierarchical data, is the solution just to flatten it and apply these techniques, or do these techniques apply equally? Because more and more we have the hierarchical.
Yeah.
For the web pages and different sources of data, which may be useful.
Yeah.
So are these techniques possibly applicable in the same way, or do we need something to figure out something?
I think we need something else. So like you can imagine like JSON or any kind of hierarchical, you can break it down into sets like this, but you're missing a lot of the context and stuff. And I don't think that's the right way to do it. Yeah. So my techniques are not hitting the robustness on the data format as well as they could. I think you can do more there. And also, if you have graph data too, treating it like this is probably not the right way to do that. So, yeah, absolutely, yeah.
I'm wondering, how do you position these two problems besides the schema matching? Can we consider these problems as the schema matching?
Yes, these are, yes, you can view these as instance-based schema matchers, but importantly, they're positioned as a search problem. I have one table, I want to find everything that matches with it, which is not the normal way, and I think Erhard's coming, of describing the matching problem. Usually in the matching problem, you start with two tables and you say what matches, or you start with a small set of tables and you say what matches. And then you might even consider the all pair problem. And so when you do it as a search problem, as I have, you can't possibly do the all pairs comparison. But yeah, so it's kind of matching as a search problem. Yes, absolutely. Yeah. Let's see, what do I want to say here? So, yeah, and what I've done so far, the user tells me, I want to join with this table, I want a union with this table. And wouldn't it be nice if you just gave them a table and they came back and said, well, using this query, you can integrate these 10 tables with what you have and gain that benefit. I don't know how to do that, but that's kind of a holy grail. How can we learn the query as well as the tables that we want? And then kind of not on the topic of what I was talking about here, data quality over open data is an interesting issue. I started off with those lovely data, open data principles, and it's pretty clear to me after working with open data repositories that we're not achieving those principles. There's a lot of junk out in open data. There's a lot of valuable information, but there's a lot of junk. So I think studying data quality over open data is very interesting. How can we quantify when a data set is clean or good, has a certain level of data quality, and is achieving some of those principles? It's a slightly different topic than what I've talked about. And I have to give acknowledgments. Of course, I didn't do any of this work. These guys did this work. So most of the work I talked about was the dissertation of Eric and Fatima. And, oh, yes. For those who don't know, most of this work was done at the University of Toronto. And I'm currently at Northeastern University in the data lab there. And we're hiring postdocs and PhD students. So come visit us there. And something I'd like to point out, and I would like you to give EHAB a hard time about. My lab in Toronto was called the Data Curation Lab, Bringing Data to Life. And I named it that like 5 or 6 years ago when I was doing a grant application. And EHAB said, oh, that's a commitment to use that word. And I noticed his talk on Wednesday uses that word. So he is finally, belatedly, on the bandwagon that curation is important. And then I have my challenge here. Can I say a few words about my challenge? And I generalize my challenge. So there's a challenge online. And this is a bit of a generalization on it. So my group used min-hash LSH to solve the join search problem. In 2018, Microsoft used a different data sketch called hyperloglog to estimate containment. And they weren't doing the data lake search problem, they were doing another problem, but they used this nice hyperloglog sketch. And then this year, the MIT folks found this one permutation hashing stuff. And so these are 3 different data sketch techniques from 3 different theory groups that have different properties to them. And we use them in 3 different papers. So here are our paper on the joinable search. The Microsoft paper was on efficient estimation of the inclusion coefficient, which essentially is containment. It's the same thing, using the hyperloglog. And then MIT just this year was using this one permutation hashing for J-card and containment similarity itself. So my challenge question is to look closely at these hashing techniques, these data sketch techniques, and compare them. And in particular, the experimental results in the 3 papers are quite different because the way we formulated the problems are different. We used open data, which has the characteristics that I outlined here. The MIT people use their enterprise data lake, which has a narrow set of requirements. And the Microsoft people, I believe, use those set similarity data sets and some internal Microsoft data sets. So my challenge is to compare at least 2 of these sketches analytically or empirically and consider when they're going to work well. So based on data characteristics, where size of the sets matters, that's characteristic number 1 for database people. Number of the sets is important. The potential cardinality skew, right? The difference. Peter Haas gives me a hard time because database people use the word skew wrong, I think. So the word skew to a database person means the difference between the smallest and the largest, right? And I think statistically that is not the correct meaning of the word skew. But I mean the difference between the smallest set and the largest set. And potentially the vocabulary size too, because some data sketches actually require a fixed closed vocabulary, and those don't work well in database kind of problems, right? That you have to know what the vocabulary is beforehand, and it's kind of a parameter to building the index, and those are bad. And then consider things like index characteristics, index creation time. So the MIT people definitely have a faster index creation time than we do, that's clear. But other things like maintainability, can you add new sets in? Can you delete sets from your index? Deletion's not as big of an issue, but you do need to be able to add new sets, and then potentially new sets with new vocabulary words. Query performance, query accuracy. Accuracy is important. Which of the sketches give better accuracy? The similarity metric supported, J-card versus containment versus something else. And any of the dimensions for a good data lake solution for those. And I've just outlined here what would be a fabulous VLDB experiments and analysis paper if you actually want to compare all these techniques together. So, and I think that's my last slide. Oh, yeah. Yeah, so the MIT people used this much smaller data set that had just 137 tables versus the ones we used, which were 51 million. And now you can argue there are problems that only require a few hundred tables, but kind of understanding the limits of which of the techniques, oops, sorry, I can't control this thing. Which of the techniques scale in which dimension, I think is a very interesting problem. Yeah. Any questions?
It's a general question.
Yeah.
Because there is also a lot of talk about data privacy and how we need to watch out what we're going to disclose, especially we can combine multiple tables. And I mean, it's kind of hide and seek now, because as people try to apply certain protection to their data and to not be able to disclose certain, we combine the tables and join them together.
Yeah.
And as much as they're going to try to apply certain fuzzying of the data or certain techniques, the more difficult this problem may be. So is it kind of hide and seek problem?
It is kind of hide and seek, but I think actually you might be able to use some of these techniques for data destruction. So at VLDB this year, Tova Milo gave a nice talk on why it was important to get rid of your data. And one of the reasons is you might be required to delete data about somebody or something. And you might be able to use these techniques to prove that in your data lake, you cannot reassemble information about a certain person or information about a certain things. So I think privacy is important, and often in data integration in general, you're often looking at what can I integrate and what is, can I prove that I haven't lost any information by translating or integrating something. And the similar techniques can be applied to privacy. Can I prove that I can't reintegrate and reassemble something? And so I think those are interesting, that can you show that using this kind of view, you can never prove with certainty that something existed. Yeah. Yeah. Yep. Go ahead. Yeah.
Going back to the question on entity resolution.
Yeah.
You see the union of two tables. Do you view two entities or two couples about the same entity being fused together, or do you see them as duplicates that just exist with the union? What is the responsibility of the union operator?
Yeah, so that's so the dirty little secret is we don't actually do the union. We find unionible tables, but we haven't actually unioned them together. Yeah, because we don't, and maybe because I didn't make Fatima do a demo, so we don't have a demo of the union work, right? Yeah. Yeah.
Extension of entity resolution, or it's different from entity resolution, and entity resolution can be like a parameter of like distinct operator.
Yeah, I guess I was viewing it as mostly the outer union at first, and then an entity resolution step applied onto it. Yeah, but it. Yeah, because the techniques we're using, we can't really recover, because the union operators are kind of matching certain entities up into ontology and things like that, but we can't recover that from the index. So I can't tell you that I union these based on the fact that these two things actually I think are the same entity. I can't pull that out of the operator. So that's an interesting question on how to do that. How to, yeah.
Resolution as like another algebraic operation. Take the tables, apply the union, then apply entity resolution to the result.
Right. Yeah, I think that's what you would have to do right now. That's a little That's right. Yeah. We can use some of the. Almaden had a very nice ER. Learning the rules for ER and things, that it'd be interesting to see if you could take the output of our operators and just automatically learn an entity resolution rule for the tables. Yeah, I don't know if you could do that.